So, have you ever stopped to think about what actually makes the modern world go round? Well, chances are it's an electric motor. They are literally everywhere. But trying to understand their spec sheets, that can feel like learning a whole new language. In this explainer, we're going to crack that code together so you know what all those numbers actually mean for performance.
I mean, have you ever stared at that little metal plate on the side of a motor, the one just packed with codes and numbers, and felt your eyes glaze over? Yeah. If you've ever wondered what separates the perfect motor for a job from one that's just gonna burn out, you are in exactly the right place.
We're going to translate that super cryptic language into real, practical know-how. By the time we're done here, you'll be able to glance at a spec sheet and know precisely how that motor is going to behave in the real world. No more guesswork, I promise.
So here's our game plan. We'll start with the motor's own ID card, the nameplate. Then we'll jump into the big three: power, speed, and torque. After that, we'll see how efficiency and duty cycles play a huge role, cover the critical electrical specs, and wrap up with protection ratings before tying it all together.
All right, let's dive right in with the nameplate. Now, it might just look like a small piece of metal, but it is the single most important source of information you have. Seriously, it's the key to everything else we're going to talk about. The best way to think about it is like a passport. It tells you the motor's identity, exactly what it's capable of, and the specific conditions where it can operate safely. Every single critical detail we're about to get into, it's listed right there on that little plate.
Okay, now for the core of motor performance. We're talking about power, speed, and torque. These are the big three. And as you're about to see, you can't really talk about one without talking about the other two. They're all connected.
So first up is power, which you'll usually see measured in kilowatts or horsepower. This is pretty much the bottom line for a motor's ability to get work done. To put it simply, a higher power rating means it can handle a tougher job or do the same work in less time.
Next, we've got speed, measured in revolutions per minute, or RPM. Now, here's where it gets interesting. A motor has a synchronous speed. That's its theoretical top speed with no load on it. But as soon as you make it work, the rotor slows down just a tiny bit. That little difference is called slip, and it's actually essential for how an induction motor creates its turning force. And that brings us to torque, measured in Newton meters. Look, if power is about how fast work gets done, torque is the raw, twisting muscle that actually does the work. It's that brute force that gets a heavy conveyor belt moving from a total standstill. And here is where it all comes together, because this relationship totally changes depending on the job. So for something like a conveyor belt, you need the same amount of twisting force, or torque, whether it's going slow or fast. But check out a fan or a pump. If you double the speed, you actually need 8 times the power. It's wild, and it's exactly why matching the motor to the load type is so incredibly important for efficiency.
Okay, so we've covered the raw performance numbers, but how well does a motor actually perform over its entire lifetime? Well, that all comes down to two things: efficiency and duty cycle.
You know, no motor is ever 100% perfect. You're always going to lose some energy as heat. And these losses, they come from all over the place. Electrical resistance in the copper windings, magnetic effects in the steel core, even just plain old mechanical friction. A high-efficiency motor is just a masterpiece of engineering designed to minimize every single one of these little losses. Now, a motor's duty cycle rating tells you how it's designed to be used. An S1 rating means it's built for continuous duty. Think of a massive factory fan that runs 24/7. But an S3 rating, that's for intermittent work, like a hoist that lifts for a minute, then rests for a few, then lifts again. If you try to run that S3 motor continuously, it's going to overheat and fail, for sure. All right, let's talk about the electricity you're feeding the motor. Because the voltage, the current, and the frequency of your power supply have a direct and sometimes pretty dramatic impact on how it performs. This table right here is so revealing. Just check this out. If your voltage drops by only 10%, your starting torque, that muscle we talked about, plummets by nearly 20%. And at the same time, the motor starts pulling more current to try and make up for it, which just makes it run hotter and way less efficiently. It really shows you how sensitive motors are to the quality of their power. A stable supply is absolutely key. So the inside of a motor is full of sensitive parts. The outer shell, what we call the enclosure, is designed specifically to protect all that stuff from the environment. And this protection rating is a huge factor for both safety and just making sure the motor lasts a long time. The most common system for this is the IP rating, which stands for ingress protection. It's a really simple 2-digit code.
The first number tells you how well it's protected from solid things, from accidental fingers all the way down to microscopic dust. The second number tells you how it handles water, from a few drips to high-pressure jets and even being completely submerged. And this slide really shows you the difference in the real world. An IP23 motor, it's totally fine for a clean, dry workshop. But for a submersible pump that literally has to live underwater for years, you absolutely need an IP68 rating, which guarantees it's completely sealed. Using the wrong IP rating isn't just a mistake, it's asking for a very, very expensive failure. Okay, so we've covered a ton of ground here. The big question is, how do we put all this information together to pick the absolute perfect motor for whatever we're doing? It really just boils down to these 4 essential steps. First, define your load. What power, speed, and torque do you actually need? Second, think about the workload. Is it going to run all day or just in short bursts? Third, check your power supply. And finally, number 4, assess the environment where that motor is going to live. If you can nail these 4 steps, you are going to make a great choice every single time. And that kind of leaves us with one last thought. With the world pushing harder and harder for energy efficiency, electric motors are right at the center of that revolution. So what's next? What kind of new materials, new designs, and smart controls are we going to see to squeeze out every last possible watt of performance? It's a really exciting space to watch. Thanks so much for joining me on this deep dive.
Let's study more and like, share, and subscribe for such more content. And comment something you want to learn.